We are on. Okay, let's figure this out. Do we have a definition for what the secant of theta is? 1 over the cosine of theta. Okay? Now we didn't define that. Somebody else defined that for us. They said, here's the secant function. And the secant function is defined as 1 divided by the cosine function. Okay, that's what it is. So that means that the secant of 11 pi over 6 is defined as 1 divided by the cosine of 11 pi over 6. So now we just have to find the cosine of 11 pi over 6. So let's see if you're doing this the way that I described. You think about 11 pi over 6 and you say, holy mackerel, that's pretty close to 2. Right? Okay, it's close to 2 pi. 11 over 6 is 1 5/6. So that means I'm only 1 pi over 6 short of a 2 pi. So if I go all the way around, that's our distance. This is a distance. Remember, that's what radian is. It's a distance around the circle that happens to match up with a particular angle. So pi over 6 is about right. The pi over 6 here in the negative direction is the same then as the 11 pi over 6 starting here and going this way. So let's see. I'm looking for cosine. So that's the x, which means I'm going to take this guy and I'm going to go up. And so which one is that? Square root of 3 over 2. So I'm going to replace that. That's 1 over the square root of 3 over 2. Okay? And this is a reciprocal. Okay? It's 1 divided by square root of 3 over 2. So it's the same as 2 over the square root of 3. And is it positive or negative? It's positive. It's on the right half. The x value is positive. So that would be correct. Okay? And we know that the cosecant is the cosecant of theta is defined as 1 divided by the sine of theta, and the cotangent of theta is 1 divided by tangent of theta. Or the cotangent is also defined as the cosine of theta divided by the sine of theta. Right? Either one of those. So that should be. Well, that way we should be able to get anything that we want to. Okay. Well, here's the plan. On Friday, we were in the middle of graphing. The tangent, and we just finished up. I remember the class period ended right at the very beginning, so we weren't quite there. So I want to do that, and then I'm going to ask if there's any other function questions, because we've hit a lot of them. Wondering if there's anything else out there, because these are our foundational tools. We got to know what those all are. And then I'm going to take a peek at a couple questions from page 16 that people had questions on there. Maybe we'll do a little discussion of what was inside there. Here, I'm planning on having us wrap up all of the pre-calculus stuff by Friday. Okay? We're not going to actually have a test on this. We're just going to move on, because for me, it was just a matter of, all right, refreshing ourselves. These are the things that we need to know, and then we move on. Okay? So keep that in mind. All right, so let's go at it. This is what we had said, that we had this circle that we were going to draw this line that touches the circle just once. Okay, and we happen to call that the tangent line. And then, if you recall, the tangent function was defined as this. We said, hey, take a radian value, whatever radian value that you have. Okay, this distance, this theta, is in radians. Its corresponding angle in degrees is this. Okay, so that's how the degrees and the radians match up. Okay, and we said that for this, the distance from the x-axis to the point of intersection here is equal to the tangent of theta. Does that ring a bell? So that's how then we would spin that spin that theta around, and we would get our values. So we said, let me pick a couple of things here. So these are the magic values: half a pi, pi, 1.5 pi, 2 pi, and so on. Then we can also go in the negative direction, and so on. Okay, so yell out some values. Tangent of 0, 0. That's us right here. The size of the line is 0. Okay. Tangent of pi over 2. Was undefined. Remember that? Because the lines are parallel, they never cross. Okay? So at pi over 2, that's where we have an asymptote on the tangent. And now you understand why we do, because this is how the tangent is defined. Now for all of the values for all of the thetas between 0 and pi over 2, they start to grow. And if you get really close to pi over 2, those tangent values are really, really big. Okay. All right, then did we cross over? Did we go past? Once you go past pi over 2, then the line actually intersects down here. Okay, and so that's why it's a negative value. Okay, so you start to get negative values immediately after pi over 2. And then when you come all the way to the tangent of pi, again, the height of that is 0. Okay. Then, once you pass pi, what happens? It starts to get these positive values again. Okay, so actually it starts to repeat right here. The graph between 0 and pi over 2 is exactly the same as the graph from pi to 3 pi over 2. Okay, and then when we hit 3 pi over 2, we again get the negative values and we come back up. So this is where the repetitive process of the tangent comes in. Okay, so what I'd like to see you observe here is that what's kind of fun about this is quadrant 1, 2, 3, and 4. If you think of your graph over here, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Think of it as linear. If you think of it as linear, meaning we're going along the line on theta for each of these, you can see, oh yeah, in the first quadrant, those were all the positive values. Then when we went in the second quadrant, those were all the negatives. And when you stop thinking about it, the tangent is positive in the first quadrant and the third quadrant. Because this is where both the sine and the cosine are positive, and this is where both the sine and the cosine are negative. And then in quadrants 2 and 4, the sine and the cosine are opposite signs. See that? Okay, so you can actually get a lot from this graph if you think about it in terms of quadrants. All right, so I got a question for you. How long does it take before the graph starts to repeat itself? Pi. Okay, pick a point, any point, doesn't matter where you pick it. Okay, if I happen to pick here, it's going to take me a length of pi before I start to repeat myself. Okay, it doesn't matter. I can pick this point right here. 2 pi later, I'm here. Okay, a pi later, I'm here. Look at the picture and tell me, why is it that it only takes the distance of pi before you start repeating yourself? Libby?
I was just going to say, like, because it's hard to explain to, like, cuts back. I don't know how to explain that.
Okay. Christina? Okay. Remember this? If I start off at 0 here, 0 radians, and then I go all the way to pi radians, okay, those are all different values. Different values. But then as soon as I just go right past pi, don't I shoot back and I start repeating? So it only takes a half a circle to start repeating on the tangent. As opposed to the sine or the cosine, how long does it take to start repeating? 2 pi. You got to go all the way around the whole circle before you start repeating yourself. Yeah.
If you move the tangent line, like if you put it like at the top or like on a different angle, you just do it, you sort of see that.
Say that again.
Like if, right now we putting the tangent line on like the side.
Here.
Yeah, and if you like move it, would it?
Oh, move it here?
Yeah.
Oh, that's a great question. Well, you'd be changing the definition of the tangent. Okay? But as this line would go here, if you still went through, couldn't you like rotate this whole thing and you would still get all the same answers? Yeah. So, yeah, what you're saying is correct as long as the rotation still is good. Okay. That's what I want to go with here. All right, and that is that. Did I show you? Yeah, I think I showed you that. Okay. All right, look at your Oh, Sam?
Sorry, it's going to bother me if I don't ask.
Yeah.
So if you took the tangent of theta minus 1 radian, so then would the line intersect where you had your ruler reduce it?
Oh, good question. What does it mean to be the tangent of theta minus 1? Right? I guess that's the... Minus a radian?
Yeah.
Tangent of theta minus theta. Well, here's how I would interpret that. If I came over here, for every value, instead of plotting the tangent, if I took the tangent of theta minus theta, then what I'd be doing is, like this is the tangent of 0, minus 0, it would still be at the same exact point. But for ones past that, you take the tangent value and then you minus the theta. So it would dip down a little bit more. Okay? And let's see, as the further we went over here, that's the bigger that the tangent is, the theta part would drag on the graph like an anchor, and it would pull every value down. So I'm guessing that the graph would kind of pull down as you go here. So it would be like this, but then if I sat on this and I was heavier each time, it would probably be a graph that looked like that. Let's graph that and see. Tangent of theta minus theta. Bitsy, you're going to be my light person. So the two on that side, there we go.
Oh,
Oh, yeah, exactly. Because I actually put theta in, so
There it is. Okay. So this is a really cool program. If you haven't heard of it, I encourage you to add it to your Google apps. It's called Desmos. Desmos, D-E-S-M-O-S. And it's really an awesome and fun graphing calculator. So look at what I was able to do. F of x is defined as the tangent of x, so that's the red one. So put on your red lens. Do you see the red? That's the tangent function. G of x is equal to x. This is our theta, okay? And so that's the blue one. That's the, and then h of x is is f of x minus g of x. So look at the green one, and you can see that's the fact that, see how I was pulling it down like I was talking about, like as an anchor. If I sat on it each time, but I sat on it heavier, this is the result. And so that's the step. It's like a step function combined with a tangent function in some way. So that is that's the deal. Yes?
So I changed the mode to the polar to actually get theta, and it's a really good graphic.
You changed the mode to be what? To polar.
And then it's like, how do you describe this? It's really, really funky. It's exciting. Because I changed
Oh,
it to x,
sweet.
so it would be theta instead of x.
Yeah. Okay. Okay. All right. We're going to do a very brief lesson on polar graph. Okay. Okay. Now, we won't use polar graph paper or polar functions, graphs at all in this year. Okay, but this is the natural learning style, right? Question comes up. Let's take a peek at it because it's actually kind of fun. Let me show you this. If I had a function where it was f of theta is equal to theta, and I was in polar, okay? I was in polar mode. What that means is when I'm at 0 radians, I'm going to plot my 0, which is right here, okay? When I go to pi over 6, I'm going to go out a distance of pi over 6. So it kind of depends on what these, let's pretend that these are pi over 6s in length, okay? Because we can define that any way that we want to. So it would be here, and then every value in between it would look like this. At pi over 4, I'm going to plot a pi over 4 distance from the origin on the pi over 4 line. At pi over 3, let's pretend this is pi over 3 distance. This distance is what we define as pi over 3. Okay? So what's happening is we're plotting the distance away from the origin for each of the radian values as we go around. Can you see what kind of picture you're going to get? Give me a good word besides squirrely. It's going to get a spiral. Okay? So if you're in radian mode, just make a function f of theta equals theta and you'll get a spiral. Okay? If you do something else funky in there, if you do a tangent, if you do the f of theta is equal to the tangent of theta, what it's going to do is it's going to plot out the distance for each of the theta values of whatever the tangent of theta is. So this is why you can get these really fun flower-shaped things in polar graphics, because it doesn't have to be a function. It doesn't have to pass the vertical line test. There's multiple values for each one. It's the graph paper that does it. Okay. Did you get the spiral? Did you try it? Okay. So that would be why you ended up where you ended up. Okay. Answer? Did that help? Okay. Let's go to other functions. Number 2 here. Are there any other things that we did not cover yet in the function packet that need covering? Because we're going to start having quizzes on this where I throw you questions and you got to tell me everything. Yeah.
General polynomial.
Okay. The general polynomial. All right, let me do this one, then I'll take other questions. Here's how this is how I want you to do the general polynomial. Okay? We're gonna modify the sheet that you have. It's all the confusion about the A and the N and all that. So what do I have there? Y is equal A times X to the nth? Okay. There's 4 cases that I really want to know. Is if A is positive and N is positive. Okay? If that's the case, give me a general description of what that looks like. Pardon me, N is, we're going to go even and odd on N. N is even. And then we're going to take all the different ones. So here A is positive, but N is odd. Now, obviously, there's an infinite number of situations for each of those, but there's a general pattern that occurs. I'll give you a hint on the first one. If A is positive and N is even, some examples here. Well, I could have like y equals x squared. I could have y is equal to 1/5 x to the 6th. See what I'm saying? So there's an infinite number of different functions. But all of these have something in common. And the thing that they have in common is their end behavior. That is, what happens on the ends. And what happens for every one of these is the graph ends up looking like this. It does this. Right? And it could do all sorts of things inside here. I don't care. Based upon, you can have, just a list of 18 different monomials as part of that function. Okay? But what I care about is the end behavior, which is what happens in the outsides. As x gets really big, and as x gets really small, being a negative going towards negative infinity. Does that help? Okay, then you do this one, and then the other 2 are A is negative and N is even. Give me a graph for that one, and then A is negative, and then N is odd. It gives me the idea that you know what those numbers, how they impact the function, the look of the function. Okay, other questions? You good on the secant, for example, or cosecant? Should we just maybe take a look at the cosecant? Okay. So the question is, how do you graph the cosecant? All right, do we have a definition for the cosecant? It's 1 divided by the sine of theta. Okay, so this is the definition of this. So that means the function is related to the sine function. It's actually the reciprocal of the sine function. So here's my secret as to how to graph the cosecant. First we graph the sine. Okay? All right, do you remember what the sine looks like? Give me magic points. When theta is 0, sine is 0. Pi over 2, 1. Pi, 0. 3 pi over 2, negative 1. 2 pi, 0. Okay, now watch what I'm going to do here. We're going to borrow those values. This is only the graph of the sine of theta. But the function uses the reciprocal of the sine. Okay? Okay, so what's a reciprocal? You just flip it. Well, what does that mean? This means that for every single value of x, okay, or theta, whatever it is, the new function here is going to be 1 over it. So the reciprocal of 1 is 1. The reciprocal of 2, 1/2. Reciprocal of 1/2, 2, and so on. Okay, so here we go. We're ready to do this now. Reciprocal of 0 is reciprocal, because I'm looking at the t-table here, and this value here is 0, so I just need the reciprocal of it. So what's the reciprocal of 0? I hear 2 answers. 0 and asymptote. Neither one of them are technically correct. I hear undefined. So 1 over 0, is that a number you can compute? No, okay? It is an undefined value, okay? Which means that we can't plot a point. And whenever we cannot plot a point, that's when we have an asymptote. See the subtle difference? Okay, so it's an undefined value. So there's actually an asymptote right here. Okay, well that wasn't very helpful. Let me go over here. What is this y value is 1. What's the reciprocal of 1? 1. Okay, I can do that. Okay, halfway up here, somewhere in here, I know I've got a value that's a half. Okay, on the sine. What's the reciprocal of a half? 2. Okay, so this is where 2 is plotted. So I'm going to plot a 2 wherever this one was. Where this one was a half, I'm plotting a 2 here. Okay, let's just keep on going here. Somewhere over here, I do also have a half. And the reciprocal of the half is a 2. Okay. Reciprocal of 0 again. That one's undefined. Okay. So, I don't have much to go off of here, so I'm going to pick some other ones. Here is like, let's see, this is 1, so I'm going to go closer to here. What's 1/4? I've got a value of 1/4 here and a value of 1/4 here as a height on the sine function. Reciprocal of those? 4. So that's why it's 1, 2, 3, 4, so I'm way up here. I'm way up here. So what's happening here for every single one of the green values, if you take the reciprocal of it, you get a new value and you plot that. What that ends up giving you is a graph And just make sure you make your circles really big. Then they go through. Now you have a graph that goes on infinitely, goes up towards positive infinity at each of these. If you erase the green part, what you have as the result, and that is the cosecant. This is where the u's come from. They're reciprocals of all of the sine functions. Okay, let's test this over here. I'm at negative a half here, so a reciprocal of negative a half is negative 2, which would be here. Reciprocal of negative 1, negative 1. I'm at negative a half here. Reciprocal of negative a half is negative 2. And again, I've got a reciprocal of 0 is infinity. So this is where the u's come in the graphs of the sine of the cosecant and the secant. If I erase all the green ones, then this is the graph that appears if you graph it on your calculator. Okay. If you want to see it for sure, graph the sine wave and the cosecant wave on your calculator at the same time, and you'll see that's where they'll touch. They kiss right here at pi over 2 and 3 pi over 2 and so on. Okay? Any questions? How would you state the domain of this function? Say it again. Negative infinity to positive infinity, and this is the domain we're talking about. And then what? Excluding all pi integers. Pi integers. 1 pi, 2 pi, 3 pi. Okay. Everybody get what he's saying? Okay. You think that's mathematically correct? Okay. This is good. This is good understanding of what's going on here because I got 0 pi, 1 pi, 2 pi. I even have negative pi here. So what I need to do is be able to say this in a different manner. Yeah. X does not equal pi over k? No. K pi? Okay. What's k? Okay. Are you telling me it's an integer? Not right now. How can we tell the person who's reading this in a very brief manner that is actually that k is an integer? K is an integer. Hey, it's an integer. What we say is we use set notation. K is an element of J. Makes perfect sense. Somebody Google it. Google the set of integers and tell us what you see. You get a Z? Yeah, that's the bummer. If you use Z2, I'll take that. Mathematicians normally align, but for whatever reason, some of those sets got different letters. Anybody else get something? Did anybody else come across J? If you Google it, you look it up. These set of numbers, instead of saying the set of all integers, they just create a variable. Then they can use it in very concise mathematics and say, guess what? X cannot equal k times pi, where k is an element of the set of all integers. I don't know. I'd have to look that one up. The origin of J in integers. I don't know. That's something I don't know. Okay, or you could use z, as we say there. What would happen if we switch this over to the secant? Okay, if we shift this over to the secant, this whole thing shifts. Okay, shifts by pi over 2, and the asymptotes are now at pi over 2, 3 pi over 2, 5 pi over 2, and they go in both directions here. So it's negative pi over 2, negative 3 pi over 2, and so on. So how do you say this set without listing all of them? Here we said all real numbers, x cannot equal k times pi, where k is an integer. How would you say that set? How do you say, well, it's every, say it again, x cannot equal k pi over 2, except it's the odd integers. And the evens don't get to play. So how do you say all of the odd integers in a brief mathematical notation? Where k is odd. So where do we say, how do we mathematically say k is an odd integer? Okay, I'm going to do a number trick with you. Everybody think of a number, any number. Oh.
Just be 2k minus 1.
Okay, all right, very good. We're going to use something that's very close to that. Okay. Everybody think of an integer, any integer. I don't care what integer. You know what an integer is, right? Okay. Think of a number. Think of an integer, okay? Multiply it by 2. I bet your integer's even.
No way.
Okay, start over. Think of a new integer. Okay, double it. Add 1. I bet your integer's, your number's odd.
No, it's not.
So what we can say here is, if you take an integer, you multiply it by 2, and you add or subtract 1, then you're going to get an odd. So 2k plus 1 times pi over 2, where k is an integer, this is how you can get every single possible odd multiple of pi over 2. K is an integer. We just played the game. Multiply by 2, add 1, you always get an odd. This is how you get every single possible odd number. Then you multiply it by pi over 2, and that's how you get this goofy list of numbers without having to write them all out. That make sense? Okay. All right. If you have not started page 27, you should be working on page 27 now. Let's shoot for